Imagine someone steals a login token inside your company network. Not your password, just a token your app already trusts. And with it, they walk straight into the system, holding your most sensitive data. No alarms, no broken logs, they just walk in. That's the kind of failure I want to fix today. I'm Ivan Šarić, and this is Secure by Default Spring Apps. How to build Spring services where security isn't something you bolt on at the end, but the default state of the system. Zero trust, OAuth 2 and runtime policies. As a quick note, I gave a version of this talk at Spring I/O 2026. Here's the plan. First, 2 ways legacy security quietly fails. The illusion of the intranet and replay attacks on bearer tokens. Then we build up zero trust on 3 pillars. With Spring and OAuth 2, we enforce it with runtime policy. And I'll leave you with a checklist you can use on Monday. Quick background, so you know where I'm coming from. I'm a senior software engineer at Revolut, going on a 1.5 years, currently in the wealth and trading department. Before that, I worked in financial crime and on Revolut's expansion into Latin America. So a lot of my instincts come from places where the threat model is very real. I also have a small LLC in Croatia called Path Variable that I used to use for freelance work. I keep it active for research. And outside the day job, I contribute to open source. For one, I contributed to the Apache Common Library and Apache Solr. I have also contributed to the Spacey NLP project in the past. So, problem number 1, the illusion of the intranet. This is the old idea that your internal network is automatically safe. Once you're inside the walls, everything's friendly. The trouble is what happens when someone gets through that outer wall. In perimeter security, one breach and the whole inside is exposed, because every service implicitly trusts every other service. Zero trust flips that. Instead of one big perimeter, you draw security boundaries right down at the workload level. You treat all traffic as potentially hostile, even your own service calling your own service. Every step gets continuous identity checks, cryptographic trust like mutual TLS, and dynamic policy. Nothing is trusted just because of where it came from. Problem number 2, and this is the one from my opening. Bearer tokens and replay attacks. A bearer token is whoever holds it gets in. So if an attacker intercepts a valid token, they can replay it, make requests with all the permissions of the user it was issued to. Picture it. A central server hands a token to an internal app or a user with very high access. Someone intercepts that token inside the network. Then they try it against a different app, the one with the sensitive data. Now, there are really 2 problems stacked here, and it's worth pulling them apart. The first is audience. A properly configured resource server should reject a token that wasn't meant for it. That's what the audience claim is for. So if the sensitive app accepts a token minted for another app, that's a missing audience check, plain and simple. But, and this is the deeper one, even with audience checks in place, a bearer token still isn't tied to who's sending it. Whoever holds the string can use it, so an intercepted token can still be replayed, because nothing binds it to the legitimate client. Closing that gap is what sender constraining is for, and that's where mTLS and certificate binding come in a bit later. This is mostly a big company problem, a massive internal network, hundreds of apps all talking to each other. So how do we fix this properly? 3 pillars. Identity, who's the user? Workload trust, who's the service actually calling your API? And runtime policy, what are they allowed to do right now in this context? Pillar 1 we solve with Spring Authorization Server using OAuth 2 and OIDC. Pillar 2 with mutual TLS plus SPIFFE and SPIRE. And Pillar 3 runtime policy with Open Policy Agent, which gives us attribute-based access. Let's take them one at a time. Pillar 1, identity with Spring Authorization Server. When you model users, clients, and services, you've got 2 token styles. JWTs, which are self-contained, and opaque reference tokens, which are just random strings you have to look up. And the trade-off is real. A JWT is stateless and self-contained. Everything's in the token, no lookup needed. The catch? You can't revoke it instantly, and without extra measures, it's exposed to that replay problem we just talked about. An opaque token is the opposite. It's a tiny random string, so on every request you call back to your auth backend to validate it, and that's a real cost. But the upside is you can kill it instantly. The backend just stops saying yes. So it's performance and self-containment on one side, instant revocation on the other. Pick for your threat model.
Comparing the latency and scaling of JSON Web Tokens, stateless, versus opaque tokens, stateful. JWTs rely on CPU for signature validation. Opaque tokens rely on network and database I/O, so their latency rises as requests per second increase.
Pillar 2. Who is actually calling your API? This is mutual TLS with SPIFFE and Spire. Here's the shape of it. A Spire server acts as your central certificate authority. Spire agents run on each node, and they do two kinds of attestation. Node attestation, the agent proves the identity of the node it's running on to the server. And workload attestation, the agent checks a local process by its selector, things like its Unix user ID or its Kubernetes service account, before it hands over an identity. Only after both does your Spring Boot service get its SVID, its SPIFFE verifiable identity document. The word workload, by the way, comes from the SPIFFE standard. It's deliberately abstract. It can be a service, a cluster, a database, any software system. So what have we actually gained? We've replaced static API keys, the old way services authenticated in a mesh. Now services get fresh mTLS certificates, rotated continuously, that both secure the connection and prove who they are. And that certificate lets us strengthen our tokens. We thumbprint the token with it, which makes the token resistant to replay because whoever intercepts it can't authenticate. Their certificate thumbprint is different. Let me say a bit more about rotation, because this is what makes it practical. Zero-touch rotation means those identities renew themselves, no downtime, no manual work. In a Spring environment with Spire, here's how it goes. Certificates are short-lived. They might expire every hour. The Spire server issues a fresh one ahead of expiry, and the agent makes it available. Then the important bit. Your workload subscribes to the agent's workload API over a Unix domain socket. In Java, through a library like Java SPIFFE. When a new identity shows up, the library swaps it into the in-memory key store your app is already using. No file on disk, no restart. So the agent serves the identity, and your app's SPIFFE library is what swaps it in. The result is continuous, secure mTLS without the usual certificate management pain.
Now let's make those tokens replay-proof for real. Two standards. The first is RFC 8705, Certificate-Bound Access Tokens. The idea is simple. Bind the access token to a specific client certificate, so a stolen bearer token is useless to anyone else.
You cryptographically link the OAuth2 JWT to the client's mTLS certificate. When the client opens an mTLS connection, the server grabs its certificate. It computes a SHA-256 hash of that cert, a thumbprint, and it embeds that thumbprint as a claim in the JWT itself, usually called X5T #S256. Then verification is two steps. When a resource server gets the token, first it checks the JWT signature. Was this tampered with? Was it issued by someone we trust? Second, it pulls that thumbprint claim out of the token and compares it to the certificate on the current connection. Match? You're in. No match? Denied. Even if the token is otherwise perfectly valid. So only the client that was originally issued the token can actually use it. There's a second approach, and it lives at a different layer. Depop, demonstrating proof of possession, RFC 9449. Here, the client generates a key pair and signs a short-lived proof, a little JWT, for every request. The authorization server binds that token to the public key. So when do you reach for which? Depop and mTLS binding solve the same problem at different layers. Depop lives up at the application layer. The proof rides in an HTTP header, so it survives intermediaries, like a TLS terminating proxy or a load balancer, where an mTLS binding would get lost. And it needs no PKI. The cost is an extra signed proof and an asymmetric check on every request. mTLS binding is cheaper per request once the connection's up, but you're managing certificates end-to-end. Pick based on where your trust boundary actually sits. Pillar-free runtime policy with Open Policy Agent. OPA is a policy engine for dynamic authorization, policy as code. It replaces those rigid, hard-coded role checks, you know the ones. Pre-authorize has role admin, scattered through your code with something far more flexible. Two things matter here. First, attribute-based access. Instead of just, does this user have this role? OPA decides at runtime using real signals, user attributes, the workload's identity, time, location, risk. And second, it's decoupled. Your authorization rules live as code in Rego files, completely separate from your application. So your security team can update and ship policy in real time, no app redeploy. Where does it run? Usually as a sidecar next to your Spring JVM, though you can also embed the policies right in the JVM as WebAssembly. The decisions are centralized in OPA, but you enforce them everywhere, in Spring security filters, at the controller or method level, in your API gateway. And because policy is just code, it lives in Git and flows through your normal CI/CD. You unit test your policies. You run syntax checks. You can even fail the build if someone tries to ship a dangerous policy change before it ever reaches production. One more thing, and please don't skip it, observability. In Zero Trust, if you can't see it, you can't trust it. You want rich audit logs for compliance, and you want your policy decisions flowing straight into your observability pipeline. That's what lets your SRE and security teams build real SLOs and alerts on top of authorization. 3 metrics I'd watch. Authorization denials per second. How often policies are blocking requests. mTLS handshake failures. When services can't authenticate to each other. And policy evaluation latency. How many milliseconds your engine takes to decide, so performance doesn't quietly degrade. Observability also lets you roll out new rules safely, canary policies. When you introduce a new, stricter policy, you don't just flip it on. You deploy it in log-only mode. It runs against real production traffic, and if it would have blocked something, it fires a canary alert. But it still lets the request through. So you get all the data on how the rule behaves with zero risk, before you switch it on to enforce. And whenever a policy actually changes, that change should show up immediately in your logs and traces. So let's pull it together into a checklist, the secure by default starting point. And that's the core of it. 3 pillars: identity, workload, trust, and runtime policy. And the thing tying them together is the mindset. Stop trusting things just because of where they sit in your network, and make the secure path the default path. If this was useful, the slides and links are in the description, and I'll add the Spring I/O recording there once it's up. Thanks for watching. I'd love to hear how you're approaching this in your own systems.